describes pretty well. So we'll go ahead and start with the announcements. Just a few reminders, and then we'll jump into today's lesson. So I'm recording now until I stop teaching the lesson. First reminder is Lattes. They're due this weekend. Please make sure if you haven't already, I've been reminding on a regular basis, I've had that up there, that you do need to pay the science lab fee for the course. So remind your family, it's paid through online school payments if you haven't done it already. The next thing is, we got a test coming up, don't we? Reminder, today is the last lesson of the unit, which means next class period on Monday, we're going to do 2 hours of practice and review. That day, I will go over with you what to expect for the test, and then we're going to do a bunch of practice activities, different activities to help us prepare, study. I'll go over some study skills because it's your first time taking a test in chemistry, and so that's going to happen on Monday of next week. Remember, Tuesday's a day off, so the next time you see me is on Thursday. And so on Thursday, not at the beginning of class, but in the second hour of class, you'll take the unit exam. And so we'll start at probably about 1:10 to give time for me to pass out all the papers, put all your phones like on the thing like normal. So you'll have an hour to take the test. So I'm just giving you a heads up. When is the test? Next week on Thursday. You got to prepare for that. For exams, there are no retakes. So that means you need to study and prepare. And so we'll practice. But today's the last regular lesson. So this is the last topic that's going to show up on the test next week. So we're concluding unit 1. What is that topic? Well, I'm so glad, you thought to ask. Let's take a look. We're going over a topic today called half-lives. And so what we're really going over is the conclusion of nuclear chemistry, which we started last class. Just a few reminders. Put your phones away if you're not using them to watch the screen. Make sure those are put away, and put your headphones away during the regular class lessons. You are allowed to, listen to music when you're doing your independent work time. So I just like to issue that reminder when we're about to start the lesson, that we're now, officially in instructional time. Okay, so today we're going to learn something called half-lives. But beforehand, let's review a couple of things from last lesson. I mentioned that I gave you this packet today. This is the entire notes printed out for you. The reason why I decided to do that for this lesson is because there's a lot of graphs and a lot of practice math questions. So I was like, why am I going to have you write down 2 definitions? I just decided to go ahead and print out the notes for you. So what you need to do, what you're responsible for, is filling in as I go along and add stuff to the screen. You should still be adding that to your notes, because if I'm writing something down, that means it's something I really want you to remember. So please make sure that you are filling in the notes as we go along, and then filling in the practice questions as we go along as well. So you have them to look back at when you're doing your homework, your classwork, and when you're studying. So a couple of things to remember before we head into today's lesson. First thing, let's write up here on our notes. What is radioactive decay? What is that process? We're going to be looking only at radioactive decay today. We're not going to be looking at fusion or fission. We're going to be looking at the radioactive decay process a little bit more. What is that? In an atom. I heard the word unstable, to stabilize. So we have some kind of unstable nucleus of an atom, right? And in order to stabilize, it has to emit some kind of particle or ray out of its nucleus. So radioactive decay is the process of an unstable nucleus emits radiation, right? To become more stable. Or like you said, stabilize. To become more stable. What are some of the radioactive particles you need to be aware of? You should rewrite them down because you need to memorize them. Right? The first type of radiation, so radioactive particles. The first type we learned last class was called alpha radiation. And what was the Greek letter for that? So there's a Greek letter. It looks like this. If you closed that, it would look like a fish, like a very simple fish, but a fish nonetheless. But it's just like that. That's the Greek letter alpha. And what's the chemical symbol for that? Remember, this is material that I'm asking you to memorize. And the best way to memorize is to repeat. What is it? 42H, right? That's called the alpha particle. This is the heaviest particle. It penetrates through the least materials. It's the easiest to protect yourself from the alpha radiation. Yes. Question?
No.
What's the second particle? Beta. And there's actually two types of beta. So the first one is beta negative that we learned in last class. And that's an electron being ejected from the nucleus. And so the symbol for that is 0 - 1, E, to say that it's an electron. That's why we use E. We're about to look at the beta positive particle. What's the beta positive particle? I mentioned what it was last class. It's called a positron, which will be mentioned in the first new slide of today's lesson. Yes.
Small question, is the line that extends from the V supposed to be that long, or is it just? I didn't know if the line was on.
This is regular B. This is Greek letter beta. I mean, I don't know how long to, I'm just differentiating. It's a longer line.
Okay.
Then it goes past. That means beta. So beta positive, that's a positron. And then the last type that you really gotta know is gamma radiation. And so gamma radiation, it's not even a particle, right? Not even a particle. Gamma is instead a ray, not a particle, gamma ray. And that is a Greek letter. It's the Greek letter gamma. And the Greek letter gamma, not the best artist, but it looks somewhat like that. It's like, I think of it like, you know, have any of you sewed? Like, have you ever sewed before? Like at the end, you have that little tiny spot where you have to get the thread through. It looks sort of like that. So it's not like a standard wide. And so there it is again with a 0, 0. Or like a weird V that has an opening at the bottom. Not exactly a V, not exactly a Y, somewhere in between. That's the Greek letter gamma. And so that tells us our gamma ray. And so that's the smallest, it's a ray. It's the most dangerous, it's the most penetrating of the three. And so this is just a little bit of a review of what we have to remember from last class. We're going to start off by talking a little bit more about positron now. And we're going to talk about positrons, and then we're going to talk about that as it relates to different types of decay. And so I'm pausing to see if most people have finished writing. And then we'll go ahead and continue. Do you need to fix something? All right, we're going to go ahead and continue now. So positron emission. This was the one type we really didn't talk that much about last class. In a positron emission, this is actually the process of changing a proton in the nucleus into a neutron. So write that out. A proton, those are the line, what you should underline. A proton is turning into a neutron. And when a proton turns into a neutron, what it releases as radiation is a positron. So the neutron stays in the nucleus, and the positron releases out as radiation. And you should write that down. This is the process of what's happening. In positron emission, this happens when a proton is converted into a neutron. So a proton will turn into a neutron. What charge is a proton? Positive. What charge is a neutron? So in order for the charges to be balanced, that's why what you're releasing is something that's positive. Does that kind of make sense? Right. Whereas in the other type of decay, which we'll take a look at in regular beta decay, right? The opposite was taking place. In regular beta decay, a neutron was actually being converted into a proton. And when a neutron was converted into a proton, what would be released? Because this has a charge of 0, this is a charge of +1, so you would need to have something that has a charge of -1, because they have to balance back out. 1 minus 1 is 0. So that's why with regular beta decay, you're getting this. And with the positron decay, you're getting this, the opposite of the electron. I mentioned that this is antimatter, which means that as soon as a positron meets an electron, it ceases to exist. Antimatter. It annihilates. Yes.
How does that happen? Like you can't be or destroy.
Yep. Yep. So that goes deeper than into chemistry. That goes into quantum physics. And so there are things we still don't understand. So maybe we just don't know where it goes. Question marks. And that's why physics gets really interesting, because physics is where all the big question marks are still at. It's like, what happens when you're smaller than the atom, when it gets smaller than the atom? And what happens as you exceed like the limits of the universe? Those things are the question marks. We know down to the atom, matter has to be created. I mean, matter cannot be, created or destroyed. Beyond that, can the laws of quantum mechanics be defied? Maybe. Yes, to be determined. But in the natural world, like the normal, can't be. And crazy, right? Science is interesting. And science is about exploring those big questions. We know the things we know, and we don't know some things still. Less things. Still more people to figure out, more people to get doctorate degrees, more people to become lead researchers, more people to get Nobel Prizes. All right, continue. All right, so here's what all of this is leading up to. We can actually look at an isotope and predict what type of decay is going to occur by looking at something called the neutron to proton ratio. And so what this means is that for atoms that are, and I'm going to highlight this number, for atoms that are small, meaning they have an atomic number of 20 or below, it turns out that most of their most stable isotopes have 1 neutron to 1 proton. Exemplified by carbon-12. We know carbon-12 has 6 protons and 6 neutrons, and it's completely stable. But if the ratio is off, if I have more neutrons than protons or more protons than neutrons, the isotope will work to balance itself back out. And that's where you're getting these different types of emissions. If there's too many neutrons, what happens? What do you think? Why? So what does the neutron turn into is the question. The neutron will turn into the other one, right? To balance itself back out, to meet the ratio. So if there's too many neutrons, it's going to turn one of the neutrons into a proton. So that's what I was saying earlier. A neutron goes to a proton. Neutron's neutral, proton's positive, so what does it release? If a neutron flips to a proton, what does it release? It releases an electron, a negative charge, right? To balance back out, which we know is a regular beta particle, 0 minus 1e. If the opposite is true, and we have too many protons versus neutrons, the proton flips to a neutron and releases a positive neutron. It releases that positive charge. And so I'll just write that down here. I had written it earlier, but it's the same idea. Proton will turn into a neutron and release a positron, because the charges will end up being balanced in the end. And then at an atomic number greater than, this should say 82, I think. It should have said equal to or greater than 83, but if we say greater, it should say greater than 82. Then what you're gonna get out of this is something called alpha radiation. This means the nucleus is too heavy itself. It can't hold that many protons. And eventually it just decomposes. So you get alpha radiation at an atomic number greater than 82. Something to point out here. 82 is a special element. That's why I remember it. Hey, what element's that? I want you to look at it.
Lead.
Lead. Lead.
Stops radiation.
Does. And actually, a lot of decays will end up with lead being a product. Like of the bigger elements, they decay into lead. It is extremely stable itself. So lead is an extremely stable element. And it's one of the heaviest naturally existing elements. Can you find on your periodic table what the heaviest naturally existing element actually is? Because you can by looking at the Cambridge periodic table. What is the heaviest naturally existing element? It's uranium. Do you see it? All the others, they don't have anything under them. They have dashes after 92. 92 is the very last element that doesn't have a dash underneath it, meaning that it has a naturally existing isotope. Fun facts. If you ever participate in something like a brain bowl and you get asked what is the heaviest naturally occurring element, it's uranium. And we use uranium. We use it for nuclear energy. We use it for nuclear power, right? So that means all the elements pretty much, for the most part, above uranium are only made either as a byproduct of a chemical reaction or made in the lab. Like they're smashing atoms into each other to just create them for a few seconds. Like I've said before, millisecond, they get happy, woo, we made it, and then it's not useful, so they don't keep it. All right, so this information is to help you to predict what type of decay would need to occur. So I can ask you a question like this, and I'm going to. You're the last class, so I'm going to go ahead and keep this and not delete it just in case you need to go back and fill something in. But let me ask you a question. What type of decay, I think you can predict this now. If I give you 14,6 carbon, what type of decay is most likely to occur? Go ahead.
Regular beta decay.
Let's see. How do we come up with that? I heard alpha and I heard beta. What should we do first to check? Find the protons and neutrons. Did I tell you that lesson 4 was going to be the most important lesson of the unit? Remember the one where we had to, find the mass number and the protons and the neutrons to get the mass number, knowing that protons are positively charged, knowing that electrons are negatively charged. Do you now see why I said that? Because if you don't know that material, you're not going to be able to do this either. That's why I said that lesson 4 was the big one for the unit. You absolutely need to know that information, and not just for this one. Like when we study unit 2, we're going to go back to that stuff again. So it's important. All right. Find the protons. How many?
6.
6. How many neutrons? 14 minus 6, which is 8. So which one do I have too much of? If the ratio is supposed to be around 1:1, protons or neutrons? Neutrons, which means the type of decay, if there's too many neutrons, it's going to want to turn into a proton, which means it's going to release something negative. It's going to release a beta particle. So you were right. So beta decay is right. So you can go back to your example from last class and you'll notice when we had carbon 14, it did decay to nitrogen 14. It's in your notes from last class. What about if I had I'm just making something up. Curium. 247. What type of decay is expected? Curium 247. What type of decay? What do we expect? Look for a curium's atomic number. What is it? You're having a hard time finding curium. It's at the bottom. What is its atomic number? 96. So just by knowing its atomic number is 96, can you make the prediction? Greater than 82. Alpha decay. Right? Because the nucleus is too heavy, it's going to fall apart. Yes.
You explain how you like that.
So that's what's here. You generally look at the neutron to proton ratio if you have small elements, meaning the atomic numbers are low. If the atomic number is higher than 82, you don't have to look at the neutron to proton ratio, you just look at the fact that it's higher than 82. So if it's higher than 82, you just know that it's alpha decay. So the answer here is alpha decay. All right, so I just wanted to work you through that exercise so that you had an idea of how to use that information on the last slide. Now we're to the major topic of the day, which is half-life. I told you that the topic for today, the title of the lesson is half-life. So we wrapped up on regular radioactive decay. There's still one more thing we needed to learn about. If you are planning to become a nursing major, I don't know if any of you are planning to actually become nurses, but I do want to bring up that you should save your notes from pre-ACE chemistry if you want to be a nurse. If you're not going to go on to the ACE class, but you go to do it at university, because what material you learn in pre-ACE chemistry is literally almost word for word the same content that you learn in nursing chemistry at the college. Because I know this because I used to work at the college and I used to do all the review sessions for students and like half-lives and radioactive decay, because there's a radiology department at a hospital. So you have to know about nuclear radiation a little bit. So this is the type of chemistry that nurses actually also have to learn as well. So just a random side note for anybody who's going into medicine, don't lose your notes. Keep your notes from this class. If you're not going into medicine, I guess, don't stress it. But some of you have expressed that you are interested in potentially exploring that field. So if you are, save your notes from chemistry because they will be useful to you. All right, now here we go. Half-life. The topic, what is that? We have discussed how decays happen. We have discussed what type of decays happen. What we have not discussed is how long it takes for the decay to occur, right? And that's the final step here. So half-life discusses how much of a radioactive sample remains after a given amount of time. So different isotopes, so you're going to want to write this down. Different isotopes decay at different rates. Meaning some isotopes decay quickly, like their nuclei just break apart very fast, and some it takes a long amount of time for the nucleus to break off the radiation. And so that's what we're going to be discussing now, is how much time it takes for different radioactive isotopes to decay. This topic is called half-life. How many of you have ever heard of half-life before? Anybody? No? There's actually, have you? Where have you heard it from? I was going to say, there's actually I want to say it's an old video game. Was it from like 2000s? There's an old video game called Half-Life. So it's been a long time though. Half-Life, a lot of times when you're playing video games, sciencey words will show up here and there. Half-life is the amount of time it takes for a radioactive sample to decompose, but a specific amount. You ready? Ready to move on? So this is the official definition. Above here, I want you to write, because for some reason it didn't print out correctly, write T1 half here. T1 half. Half-life is represented by the letter T and then a 1/2 after it, same amount of time. And it is the time required, the length of time required for 1/2 of all the radioactive nucleuses, which we call nuclei, to decay. That's why it's called half. Because you're always going to have half the amount that you had before at this specific amount of time. So if I told you, for example, that the half-life of iodine 131 is 8 days. And you'll see this later on in the lesson. It's going to show up in a chart.
Like the full life of that would be 16 days?
Yeah. That's not how to understand it. If I told you that the half-life of iodine 131 is 8 days, what that means is that after every 8 days, I'm going to have half the amount I started with. So what does that mean? As I said, you might. That's why I asked. If I start with 100 grams, after 8 days, how many grams will I have? I have 50 grams. So what would happen after 16 days? I heard it over here first. You're absolutely correct. 25. All right. So does that kind of communicate what's going on here? I start with a radioactive sample. This amount of time passes. I now have half. This amount of time passes again. I have another half of what I had before. So the amount is decaying, meaning somebody asked in the last class, it's less radioactivity is coming out. In a way, you could think of it as if it's dangerous, it's becoming less dangerous over time, because as it's emitting radiation, that radiation is gone. It'll emit less and less radiation over time. Yes.
Can you say that was carbon 14 was like really slow?
It is really slow. You'll see it very shortly.
It's like when medicine becomes less potent.
It is an idea. It's a similar idea to potency. Absolutely. It becomes less potent over time. Less radiation is being emitted over time. If we think back to, I don't know if I've mentioned in this class, Chernobyl. There was a power plant meltdown in Chernobyl back in the 1980s. And because of the radioactive isotopes that are in that area, the type of radiation, they estimated 10,000 years before people can live in the radius again, in like a certain radius from Chernobyl, because of how much radiation there is and how long it takes it to decay. And so it depends on what you have. Yes.
Accurate?
What?
Right? Accurate.
Well, would you want to test it? I mean, it's a question. I would like to assume that they're accurate and not go to that area. I would not like to test that myself. Makes sense? They've determined the radioactive rate that it'll be safe is 10,000 years, which basically means my lifetime, your children's lifetime still won't be livable in that radius outside of Chernobyl. So it's all gated off.
And that's still the capital?
No.
Oh, no, they switched it. Never mind.
All right, so this chart right here, it says do not memorize. So what should you write on your notes? Do not memorize. I am not asking you to memorize this chart of all the possibilities of different isotopes and what they can do. I have it here just to discuss. For interest notes that there are radioactive particles actually all around us that are commonly used for different reasons. Some are dangerous, some are not very dangerous, depending on how much radiation they emit and if it's targeted correctly. Yes. I'm sorry? You didn't get the notes, you mean? Maybe you were in the bathroom? Okay, so California, does it say what type of radiation? Alpha, could you have predicted that? Californium,
Was it
element 98. Reason it's named californium is because that's where they made that element. We're not very, it's either used to cook,
California.
not very creative. It's usually either, those big elements are usually either sciences that you want to commemorate, the scientists who made it, or the place where it was made. So like there's like a Moscovia
Yeah, like I once heard
in
like
a Tennessee, or Tennessee, actually.
I heard a dumb one that was like mercury, like mercury.
No, that's a full element.
I know, but they were no, because I heard someone say that it was named after Curie.
Oh,
And I was like, no, that's not right.
curium.
Yeah, curium. Was
All
named
right.
after her.
So let's talk about some of the uses. Again, do you need to memorize all of this?
No.
No, this is just like for your information, real life application type deal, because it helps us to understand, oh, these isotopes, they do exist. We use them for different things in real life. Californium is used to test luggage for hidden explosives. Where would that happen? In the airports. So when you put your luggage to go into a machine, could have californium that's coming out to test if there's explosives. Used to gauge moisture levels of the soil for construction. A lot of these are used in industry. Did you know that people who go into industries like, mining and different types of, construction are more at risk for certain things like cancer because of their exposure to carcinogens, radiation being an example of carcinogens. And so they have to wear, depending on what they're working with, protective gear. People didn't know about that back in the day, so their lifespans were shorter. All right, cesium, used in cancer treatment. So have you ever heard of radiation therapy? This is when they'll target cancer cells, and it takes multiple, tries with it, but it'll target cancer cells. They'll send in a radioactive particle, and it'll kill cancer cells. The problem with both radiation therapy and chemotherapy is that sometimes it's not completely selective to cancer cells, and also will make the patient very sick. So people usually who undergo those therapies, they actually feel worse from the therapy, even though it's helping them, than without it sometimes. So cobalt, used to sterilize instruments. We mean in medicine, you should always work with sterilized instruments. If you are planning to go into medicine, if you treat a patient with a non-sterile instrument and then they get a bacterial infection, you could totally get sued for that. And it's just bad practice. Curium is used in mining. Iodine is used to diagnose and treat human diseases of the thyroid. So which only has a half-life of 8 days. So does that mean that you can just have it sitting around? You cannot just have iodine going. It has to be created and then shipped out as quickly as possible for it to be able to be used. But I know about this one because I have several family members that have thyroid disorders. My grandma had a thyroid disorder, hyperthyroidism, and she was also allergic to iodine. So what did that mean? The doctors would always want to treat her with iodine, but she would get a severe allergic reaction. So she couldn't use that tracer for any kind of diagnostic or treatment. And plutonium-239, obviously that's used for nuclear purposes. And so you can see here some of their purposes and their half-lives. Yes.
Radioactive elements are the only ones that have the possibility of having a half-life.
If it's radioactive, it has the possibility of having a half-life. If it's not radioactive, it has no half-life. That is a great point. Yeah, so this is radioactive isotopes have half-lives. Notice that they could be short. Some of them could be seconds, and some of them could be millions of years. This is just a selection of some. I have a much larger chart than this, but I didn't want to go through all of them, so I just gave you a selection of some. All right, so now what are we going to do with this information? First thing, we have to learn how to read a graph correctly. So, graph to left represents the decay of a radioisotope. Has anybody ever heard of exponential decay before? The other classes all said they did. This is an example of an exponential decay. So, looking at the graph, can you figure out what is the half-life? So once again, what are we saying when we're asking for half-life? What does this describe to us? How much time for what?
Half the lifespan.
How much time for the sample to decompose by half? So whatever amount I start with, the time I have half of that original sample. So what would I need first to figure this out? I need to find my initial mass of my radioisotope. I need to find out how much I start with. By reading a graph, how much would I be starting with on this graph? 10. And how do we know that? This is my initial amount. That sounded very mathy. I heard y-intercepts. So when the time is 0, the amount is 10. At a time of 0, that's what we call our initial amount. So our initial amount equals 10 grams. What's half of that? So half of 10, right? These numbers are not too crazy. Try to start you off with some easy numbers. So 10 divided by 2 is? This would be the amount at the half-life. So this would be the amount at the half-life. Okay, by reading this graph, how can we figure out how much time that is? What is we do now? Go ahead.
Go to 5 on the
To 5.
line,
And then go over to the line where it meets, right? It doesn't have to be perfect. They're rounded, so you just find what's closest. And then you have to meet it on the time side. What time is this? 30. The answer's 30.
You were blocking 4 and I thought it said 25.
Oh, sorry. So 30. 30 is the best here. Answer. So that means after 30 years, I have half my initial amount. What would happen after another 30 years? What happens at 60 years?
yeah.
What do you predict should be that amount? 2.5, right? After every 30 years, you have half the amount you had 30 years ago. So it goes 10, 5, 2.5, and then it keeps halving. Does that make sense? Half, then half, then half, then half. So that brings us to our equation for the day. I know you're all so excited to see the exponential decay function. I guess I ought to bring up about this moment. In chemistry, this is actually one of the more mathy units of the year. We have 3 formulas that we covered in this unit. The first one was density, if you'll recall, density being mass over volume. The second one was the atomic mass calculation, which was mass times percent over 100. Did that for each isotope. And this is the third one. You'll be very happy to know, if you aren't a big math fan, that we aren't going to have much math for the next several units. So units 2, 3, and 4 don't really have a lot of math in them. There will be counting. There may be one formula, but it'll be less. So just, I hope I haven't made you think that this is completely a math class, because it's not. But there is some math formulas in this unit of study, like to just start us off in the year. And we had measurements here. But there's a little bit of math. What did I tell you the percentage was approximately? 30 for Cambridge, 50 for American math, 30% for Cambridge math. So it's about a third math class, not all math class. But we use our math always in application to solve a problem. Every math question we have relates to the actual concept that we're learning. So here, we're talking about an exponential decay function. So this is the formula, and unfortunately, you either have to memorize this or understand the concept to be able to solve questions. I'll give you an alternative method for those of you that are allergic to math. And by that, when you see a math formula, you go, yes.
Will you also be teaching us how to do this in the calculator? Or I don't think
Well, I mean, I've already talked a whole day of going over how to put this in the calculator, but yes, you'll be able to put this in the calculator to solve for easy questions. All right, so we first have to go over what do each of these things mean. What does A stand for in the exponential decay? A stands for your final amount. of whatever the radioactive material you have is. So after such and such time has passed, how much do I have left? So that's why they said amount remaining. Amount remaining at the end of the time passed. Final amount after whatever time has passed has passed. A0 stands for how much we start. You should write that down. That's how much we start with. The initial amount at the beginning, before the decay begins. And the letter N stands for how many half-lives have passed. Remember that I mentioned in that last question, after every 30 years, we would have half of what we have. So this discusses in that scenario, how many of those 30-year intervals have happened. That's what N represents, is how many half-lives, how many of those amounts of times have passed. For the purposes of pre-ACE chemistry, N will be a whole number. So this will be a whole number exponent. Because we're not going to complicate the math in this class. For the purposes of reality, could you have time frames that are in between half-lives? Yeah, in reality. But we will keep the math simple in this class because you'll see why. Yeah, you'll see. Continue. All right, so the first couple of questions we do, I'm just going to show you how to plug the numbers in the formula, how to plug it in your calculator, and we'll directly solve for one of the things that's being asked for. Then, because the math is actually quite difficult to solve for N directly, I'm going to teach you an alternative method to using the formula for those types of questions, which I'll show you shortly. So let's get to it. Let's get to the math. As is usual in this class, when we have math, we have some type of problem we need to solve. So let's take a look at the question. They will always be word problems. I apologize, but we're solving some kind of problem. So it says the half-life of zinc 71 is 2.4 minutes. This means this is the amount of time that passes for me to have half of what I started with. Then it says I have 100 grams at the beginning. That's how much of the sample I start with. How many grams would I have after this amount of time has passed? And so let's start by writing the formula. So let's write our formula. You should practice whenever you're studying for science or math. You should always write your formula that you're going to use before you start solving the question so that you know what you're going to input. So A equals A0 1/2 to the N. First of all, this is T1/2, right? That's our half-life. That doesn't show up here at all. Like 2.4 and 7.2, those amount of times don't show up in this formula at all. What number here is in this formula? The 100 grams. And what is that? That's A0. So at this moment, I only know I have this. What am I solving for? It says how many grams at the end, right? At the end of that time. So I'm going to put a question mark above A. That means I'm solving for A, which means I have to have enough information to figure out N. Let's talk about it, too. How to find N, which is number of half-lives. Some of you will know this off the top of your head, but I'm going to give you a little formula just in case you didn't get it off the top of your head. If you did get it off the top of your head, what did you come up with for N?
The answer?
Yeah, the answer. 3 is the answer. How'd you do it?
I divided 7.2 by 2.4. That's what we're.
Okay, so you did exactly what I'm about to say. To find N, what you have to do is the following. You take your total time that has passed You have to figure out which amount of time is the total time that has passed, and you divide that by the half-life. How much time for your sample to decompose by half? So then what are the two numbers I divide then to find n? What is my total time? 7.2, and I divide that by 2.4. If you get confused which time to divide by, the bigger number should be on the top and the smaller number should be on the bottom, because what did I tell you about n? It has to be a whole number. So if you do the division and you get a decimal,
That's wrong.
flip them around. Do it the other way, because you did it wrong. So that's why I'm giving you clues as you're going along, so that when you're doing questions, you can check yourself to see. All right, so this is 3. Are we good with this being 3? And it's 3. 7.2 divided by 2.4. You can check that in your calculator. So now 3 is n. Do we have enough information to solve the question? Well, we have everything except for the missing variable, right? So we do. So 3 will be solved. We're solving for a. Plug in a 0. That is 100. Multiply, if there's no sign here, but there's a parentheses, that means you're doing a multiplication. So it's 1/2 raised to the power of
3.
Plug this in your calculator. I have taught you how to plug this in your calculator. Remember to put parentheses around 1/2 and then put the little caret, like it's a little sign that goes up for the exponent. Try to see if you can get the correct answer in your calculator. I'm going to tell you what the correct answer is so that you see what you're supposed to match to. What'd you get? 12.5. 12.5. And it's 12.5. Check to see if you get that though. If you don't get 12.5, when you plug that in your calculator, let me know because I can help. All right, so we're going to try one more question like this. And then I'm going to go to the second method to show you for those of you that are allergic to math. And the reason I'm going to show you is because the question that follows it is difficult even if you like math, because you might not have learned like that math yet. All right, ready for the second example? So second example, let's see what we're being asked. Carbon 14, wasn't that just asked just a few minutes ago? Carbon 14 emits beta radiation, decays with a half-life of 5,730 years. For the sample to decay by half takes 5,730 years. You have 200 grams to start. First question, how long is 3 half-lives? It's 5,730 years for 1 half-life. How long is 3 half-lives? Go ahead.
17,190.
And how did you do that?
By multiplying 5,730 by 3.
So if this is the amount of time for 1, you multiply by how many have passed, which is 3. And I get 17,190 years. That's the first question. Second question, unrelated, is how many grams of the isotope remain? What am I looking for there? If it says how many remain, what am I looking for in the formula? At the end of 3 half-lives, so we have that information. I guess to help you figure it out, we should start by writing the formula. So let's write the formula first, and then we'll take a look at what we have and what we're looking for. What do we have? Do we have the final amount? No, that's what we're looking for. Do we have the initial amount?
Yes.
It's 200, right? So 200 should go here. and then 1/2 to what exponent?
Three.
So then that's the math. 200 multiplied by 1/2 to the third. What do you get? 25 grams. That's it.
It's also good.
Do you plug it in your calculator? Could you reason another way to have done this instead of the formula? Knowing that I have half after every half-life, and I know that it's been 3 half-lives, what could I have done, Isabella?
We would divide it 200 by 2 and then take the answer and divide it and take that and divide it by 2.
That's exactly what you could do without a formula. And you would get the same answer, right? So if you know that 3 half-lives have passed, remember that each half-life, you have half. So if I take 200 and divide by 2, I know that after 1 half-life, I have 100 grams. Then if I divide by another 2, I'll have 50 grams. And if I divide by another 2, I'll have 25 grams. 25 grams is the final answer. So I'm saying that you could either use the formula or you could sort of reason it out. And so the second method I'm going to teach you is how to reason it, just in case the math becomes difficult. And I will tell you where the math's going to possibly become difficult. But let's take a look at the strategy. So we're skipping this question. For those of you that worked ahead, if you solved this question on your own, because I know that I have told you if you would like to work ahead, you can. The answer here was 0.3125. So if you did it on your own, that was the answer. If you want to do it on your own later, you can. But I'm skipping this question because it's actually the same thing. The last 2 questions have been like the same exact setup. So we're going to move on to the other thing you have to know, which is what if the math becomes difficult? What can you do instead? And I started that idea right here. You could actually reason out what's going on. And so method number 2 is to do something like creating a chart to see what's going on. And so I want you to fill this out just to see how could you mentally reason through solving all of these questions. Because you technically don't have to have an algebraic formula as long as the numbers are easy, like the half-lives are all easy. So at our initial amount, start with that. We don't know, every question will have a different initial amount. How much time will have always elapsed when you have your initial amount? 0. This is at a time when no half-lives have passed, right? And so let's take a look at what happens as each half-life passes. When each period of time passes, 1 half-life passes, how much of the initial amount must I have? Half. So you would take it and divide by 2. Or say you have 1/2 of the initial amount. Every time, right? And the time elapsed is whatever the time is of the half-life. So time of half-life. How much time it takes for that time to pass. All right, move on to the next line. A second half-life has passed. How much amount would you have? A half, which is?
1/4.
You would divide by 2 again. And some of you got that right off the bat. It's 1/4. You'd have 1/4 of the initial amount. But you could just remember, keep dividing by 2. How much time would this be at?
Half-life times 2.
The half-life time times 2. Do we see the pattern? What happens at the third half-life? What would happen to the initial amount?
You get 1.
It would be divided by 2 again, right? 2 times 2 times 2 is actually 2 times 2 is 4 times 2 is 8. It would be 1/8, the initial. And there's a pattern. You keep dividing by 2. You keep adding 1 to your amount of half-lives. And then for your total amount of time elapsed, what would you multiply by? Here. It would be the time of the half-life times 3. So I'm going to show you in the next question why we would opt for a reasoning strategy like this instead of just going to the algebraic formula. And then some of you may opt for this every time. If this makes more sense to you, then use this strategy. I don't fault you for using either. You can use either strategy you like. I'm here to give you strategies as your teacher because I want you to be empowered to solve questions correctly. Yes.
Can I just abbreviate half-life to HL? Like
I would abbreviate it to T1 half
that's what I
because it's a formal abbreviation that it will show up as. But because some people are still working on symbols and symbols can be confusing, that's why I wrote it out. Continue. All right, so this question right here that's coming up. If your reasoning skills, sometimes it's difficult to reason, the formula is going to actually get you very, very stuck. So let's take a look at how we can solve this question, creating the chart first. So I can show you that, and then I'll show you what it looks like with the formula. So this is the hardest type of question you can have. So I would say, like on the exam, I wouldn't put any more than one of these because it's the hardest type of question you could have. Let's take a look. In 6.2H, which I think wherever I got this from, they should have written HR. What amount of time is this supposed to be? Hours. I've never seen hours abbreviated as just H. I've always seen it as HR. So I would just fill in the R's. In 6.20 hours, a 100-gram sample of silver 112 decays to 25 grams. The question is, what is the half-life? So you may already know how to do this without doing anything. Hold your answers. Hold your answers. But if you understand what's going on, 100 to get to 25 has to be halved how many times?
40 times?
I hear different answers.
Or 2
Oh
times?
no. Okay, so we're gonna create a chart. That's rough. I heard 2, 3, and 4. We'll go over the answer shortly. We're gonna go over that answer shortly. Create chart. Here's the order that I would write it in. I would do the amount first, then I would do the half-lives and the time passed. So time passed. So how much time has passed? Total time passed. And number of half-lives. All right, what's my initial amount? In the question, do they tell us our initial amount of material?
Yes.
Yes, it's 100. So start with 100. This is at a time passed of 0, right? It's what we start with. And a number of half-lives of 0. So let's go through the strategy. We need to go down from 100 to 25, but we can't go directly there. We can only go half at a time. So we would go from 100 to 50. We don't know what time passed that is. We don't. We don't have that information. But we know that would be the time of one half-life. It's asking us for the time of the half-life. We don't know that information. So we don't know this, leave it blank. What can we do though afterwards? 50 can go down to 25. I divide by 2. Do we know how much time passed now when I have 25 grams in that question? Does it tell me the amount of time to get to 25 grams? It says in 6.2 hours, 100 grams decays to 25. That means that 6.2 hours have passed to get here. Does that make sense? It's always the reading that's the problem. How many half-lives? 2. This is enough information to solve the question. if I know that 6.2 hours is 2 half-lives, and I know that each half-life is the same amount of time, then what would I do now? Go ahead. Divide. Because remember, this would have to be a smaller number. Right? You wouldn't go up and then go back down. So it would be 6.2, but the idea is you have to use the 2. 6.2 you would divide by 2. Why? That would tell you there would be 3.2 hours in one half-life, right? So this answer is, or sorry, 3.1, I can't math. 3.1 hours in one half-life. Is that answer here? Yeah. It is here. All right. So we can reason that answer. And if you've gotten 3.1 beforehand, you can pat yourself on the back. Yes.
It's basically like the amount of time that passed over how many times you divided A0 by 2
Yeah.
to get A.
Yes. You can totally use that to come up with it. Now, what if you blindly followed the formula that you didn't know this method and you just were like, I'm just going to use that formula I learned every single time. So what if you use the formula? What would be the problem? And why am I suggesting not to use the formula here? So I'm suggesting not to use the formula if you're being asked for the time of the half-life. Why am I bringing this up? Because I think it's important to go through that exercise, that thought exercise. What if we use the formula? Could we have come up with this answer? I could. My question is, could you? What if we use the formula? What would we be plugging in?
25 equals 100 times 1/2 hour of 6.2 over blank.
So we would have, you're on the right track. We have A, that's 25. We have AO, that's 100. You knew that N is the total amount of time passed divided by the half-life. That looks very terrifying to most people, so we're just going to leave that as N for now and go look at the next thing to do afterwards. This already might have most people stumped. Why? Because this is an exponent. How many of you have ever solved for a variable and an exponent?
Don't you square it?
No. Square root only applies if you have x squared.
Oh, yeah, because you have to do
We don't know that that's squared. We're not sure. How would you solve for an exponent? You technically, most of you won't know that in this class. I am well aware of that. Why? Because the classes you would figure this out in are either college algebra in a dual enrollment class or in algebra 2, which here is pre-AICE Math 3, but it's done in April. So I'm assuming that you don't know the strategy, which is why you would get stuck here. You would pretty much get stuck here. What do you reason? What could you think to do though? Like, what could we try to do? So what? Well, first you have to divide by 100. You have to divide by 100 on both sides. So you get 25 over 100. What does that simplify to? Anybody know? Your calculator can do it for you if you have a Casio. It's 1/4. So 1/4 would be 1/2 to the n. What could you do now to solve for n? The concept is, we want to know, and once I tell you the concept, you might figure this out. How many times do I have to multiply 1/2 by itself to get to 1/4?
Oh.
Isn't that the concept?
Oh.
To find the missing n, you need to know, because this is, exponents mean repeat the same thing over and over again. How many times would I need to repeat this to get that? 2. Yes, 2. But if the official math to do this, most people, your math teacher will teach you it's this, 1/2 squared, because it's 2 squared. And that's 1/2 to the n. And n, once the bases are the same, you can drop them, you'll learn. And the exponents just equal each other. And it'll be n equals 2.
See, I totally.
You totally knew that? Mm-hmm. I should survey my 120 pre-A students and see how many knew how to do that. I'm thinking the number's real low. But you don't have to do it this way, right? So this tells me the 2. I know 2 half-lives is that amount of time. So then I would still get back to 6.2 divided by 2. And it would give me 3.1, which is my answer. I think this method is easier, personally. I think it's easier for the students. But if you are into math, that's your thing, then you may opt for this method. You could use it. This formula can technically work for everything. You just have to know how to use the math. So up to you, up to you. All right, good to continue? We have one more question to do together. One more. For the last question, would you like to see the chart again, or would you like to do the formula? Because the next question is actually easier with the formula. The only time the chart is the easiest thing to do is when you're solving for n, or something that's involved with the time. Otherwise, if you're just looking for amounts, the formula ends up being an easy route to go. So in this last question, they asked us for an amount. So the formula should serve us well. A equals A0 1/2 to the n. Remember, the more you write it out, the more you're going to remember it. That's how information is. So one, we've got our formula. They're asking us for grams after a certain amount of time. And I just remembered that this question is missing one piece of information. You technically can't solve this question right now. So if you were trying to work in advance and you got stuck, it's my bad because I forgot to give you a piece of information. I realized it when I was solving all the questions. I had already printed the 120 copies, so. But the missing piece of information, go ahead and fill it in now. You need the half-life. You need that the T1 half is 1600 years. Without this, and I have to give this to you, so obviously on the test I would give this information to you. You need this, so also need it.
1600 or 16?
1,600. 1,600. So, I'm now giving you the half-life. I'm giving you the total amount of time. I've given you the initial amount. What's the next thing we should do before we can just plug in the formula? We have to find n, which is the T1, it's the time passed divided by the half-life, the T1 half. That's what n is. So how much time has passed in this question? 6,400 years. And how much time did I just write was the time of the half-life that you needed to solve this question? 1,600. So divide those two numbers, you get 4. Then we can plug everything into the formula and then into our calculator. So 3 is to solve. It's going to be A equals, our initial amount is 50. 1/2 to the 4. If you get the right answer here, you'll get 3.125. Check in your calculator, see if you get the same thing. I have a question for you afterwards. We're about to be done. This was the last slide. But I have one last question before I stop recording. Is there a way you could have 50-50 your answer choices here? Are there 2 answers you could have immediately gotten rid of? Yes.
You could have gotten rid of number 2 first because it's greater than the starting amount.
Does that make sense? If the whole point is decay, that means if this is my starting amount, my amount must be less than that. So at least you could take 1 out here. And I'd probably also take out 25 because that's the amount of 1,600 years. But if you have an amount as a final amount option choice that's a bigger number than your initial amount, that doesn't make any sense because it's decay. So you could take that answer choice out. The answer here is 4. So we're done with the lesson for the day, so I'm going to go ahead and stop recording at this time so that I